Our next speaker, without further ado, is Paul Stackhouse. Dr. Stackhouse is a good friend and colleague at NASA. He has all the funds and all the money. But yeah, so he's been a lead scientist for quite some time at NASA doing surface radiation budget type work, and leads the innovative work as it relates to that in climate processes. So without further ado, please take it away.
What program was your granddaughter?
It's the Interdisciplinary Earth Data Science Program. Jared is the Anton is the program officer.
Okay.
Told you the money.
Yeah. No, I don't have the money. Not yet. Maybe eventually. All right. Okay. Well, if I'm successful with this talk, as I sat here for the day and a half, I noticed just different uses of different types of satellite data. And I just thought, maybe the audience would really appreciate just kind of get an idea of the breadth of NASA's program. And so I rated slides from management, earth science, and tried to generalize a little bit. But I will emphasize a new emphasis within NASA, which is Earth action, right? So we've talked about data at Earth action. So I'm going to talk about data. And it's a problem, in a sense. It's great, but it's a great problem, but it's a big problem because there's so much of it. So the question is, how do we use that? And so this new program trying to link the research to the actions is something of a new emphasis within the program, and it's kind of a reorganization of old program. And so then as a kind of an example of that, I'll show you what we've been doing in my own project. So it's kind of like broad to narrow. And then I'll have one very ordinary slide that talks about, okay, this is really about innovation and the future. So where can AI and machine learning help? And as I go, if I'm successful, I will point out those areas. First, you might be thinking, all right, what's NASA doing here as energy, right? Why is NASA involved in energy? Shouldn't DOE be here? Where's DOE? Anyway, we have all these satellites, and this top figure here shows just the constellation of satellites. Many of you are familiar with these satellites, and I'm going to highlight a few of these. But the point is all these satellites are collecting data for different environmental variables and atmospheric variables, whether it's clouds, it's gaseous constituents, or particulates, or aerosols, or surface properties. And so each of these are usually aimed toward environmental variables or atmospheric variables needed for Earth system modeling, Earth system understanding, for instance, the atmospheric composition and its changes, the weather and atmospheric dynamics, climate variability and change, the water cycles. Can we close the water and energy cycles? That's something that I have been working to. How about the carbon cycle and the ecosystem? What about the Earth's surface and interior? So these missions are to feed this science. But the reason we're here is because they also feed important applications that help inform decisions and planning and the sorts of studies that we've seen for these last 2 days. So we're striving to improve data access and application to research and societal benefits. So I wanted to highlight one of the missions that I work on. This is called Ceres. You might not have heard of it because it's not high resolution, but this is a mission that's essentially monitoring the integrated heat of the planet. In other words, we measure the reflected energy from the sun out of the Earth atmosphere system, and also the thermal infrared emitted energy. So the balance of those two essentially determines the energy balance of the planet. If you have more in than out, then you have heating. If you have more out than in, you have cooling. So this mission has been going since 2000, and this is a plot here showing that the integrated, so this isn't just surface temperature, this is the whole Earth atmospheric system, is saying that we have a net increase of energy by this rate. And in fact, over the last 5 years, it's been increasing So it's somewhere around a half a watt per meter squared per decade. Increase the heat on a global, which is multiple petawatts of energy that's primarily being stored in the oceans, okay? So this mission measures that, but it also, because it tries to incorporate all the clouds, it has information on the clouds, and we have information on aerosols incorporated and gaseous properties. So that means we can compute the energy from the sun that reaches the surface of the Earth. So in concert with this and the well-calibrated, precise measurements, we can actually do the surface radiation budget and talk about solar radiance trends, regional trends, changes in those quantities, and how they're due to different clouds, changes in clouds. Are we seeing, for instance, of the oceans, we're seeing less stratocumulus clouds. So it's more energy into the oceans, okay? So we're looking at as a function of attributing why we're having changes. This is a new mission. It's up. It's first taken data. It's called SWOT, the Surface, Water, and Ocean Topography Mission. Very high resolution information. And the reason I brought it to your attention is so this is the ocean eddies. It's primarily aimed at looking at temperature and heat fluxes of ocean and eddies and oceanic uptake of carbon. But it has multiple applications because it's also used to map rivers and reservoirs and lakes. So you can determine the height, since the radar, it can determine the height of the water surface. And then for rivers, you can determine the slope and the channel width. You can do river discharge. So this is something that is a mission SWOT you should be hearing about, and hopefully will inform. So we have various different people already doing applications with this. So I think this one was here in Texas, looking at the various different reservoirs and their levels. This is about the flow of river in the Nile, and then even assessing floods. And so this information is being validated right now and should become public soon. Then we have another mission. This is currently up. Many of you know about it. I think our moderator knows something about it. And this is called Tempo. And so this is hourly. You can see here this little cool graphic here. I had to throw a couple cool graphics in. But this is part of a constellation of geosynchronous satellites. There's geosynchronous satellites doing hourly NOx and SOx and particular pollutants. And I'll show you some of what we plan to do with Tempo data in a little bit. But this is becoming available. First data has already been released. It's brand new. And it provides some opportunities. I didn't want to list out a bunch of missions, but I did. But I wanted to kind of give you a sense of the program. And this is not all the missions. I showed that fleet diagram on the first slide. This isn't all the missions. There's a lot of smaller, very targeted missions. But I want to kind of give you a sense of what. So I've already mentioned Ceres, and there's a follow-on mission for that. GPM is the Global Precipitation Measurement Mission with an iMerge data product that's doing global precipitation at 10 kilometers, okay? It's a new version, so you have to go back. One of the things that I'd point out is that these data products, they get processed, then they get reprocessed. So you really do, when you make decision-driven changes, make sure you have the latest versions of these. I wanted to mention that Ceres, we're doing a new version in Ceres. We're doubling the resolution. And we have a lot of machine learning to improve some of the algorithms in terms of the inputs. So we're incorporating machine learning in that as well. So we have the global precipitation. So these ones here have to do with moisture. We have the GPM. Looks like I had reordered these, but this is the old one. So we had GPM, SMAP. SMAP is currently up. It's soil moisture. We already saw some presentation on groundwater. Hopefully that, if they're not using SMAP, that would be a good resource. There's also, so I mentioned SWOT, there's also GRACE, measuring changes of the gravity. fields, which is moderated by groundwater, deep groundwater. So we have water emissions, we have the particular emissions in the air, we have the orbiting carbon observatory as well. PACE is going up next year, which is going to be looking at aerosols, but ocean color and ocean life, but it also is going to have global clouds and aerosols information. There's a new Earth System Observatory, ESO, that's of an emphasis on aerosols, but not just aerosols, their role in clouds and precipitation. So you can see the physics there that's being treated, that process, but clearly there's going to be global distributions of these quantities produced, which should be improved. The NISAR data, this is a project with India and the synthetic aperture radar. So we're looking at processes like surface vegetation, ice, and the deformation of the surface. So just a quick, at NASA Langley, we're a coastal center because we're right in Hampton, Virginia, right next to where the James River and Chesapeake Bay, and we're sinking, and the sea level is rising, right? So double the trouble. All right. So Landsat next. The people are really using Landsat. 2030 is the new instrument here. More than double the spectral channels, and then a little less than the frequency. And so that one's under development as many other more missions. And so I mentioned that this is really to support Earth system science. Maybe some of you have heard of the Global Modeling and Simulation Office and their work there at NASA Goddard. We have a Goddard colleague here. And they have the GS modeling system. Maybe some of you have heard of the simulations called MERA-2, or somebody mentioned GLDAS already today. So GLDAS is a NASA global land assimilation data system. We've got the chemical transport models and the global climate modeling. So I was actually at NASA GIS in New York City last week and got some updates on their efforts. But that's primarily what the missions to support, but we see that there's action. So I'm going to go a little faster because I see the time. I asked for an hour, but so there is. I think this is where we talk about innovation. What can it do? Look at the data. This is in petabytes. This is the current holdings of NASA archives under the 50 petabyte here, and just 2 years ago, and by 2025, already up to a quarter of what's the next one? Exabytes, right? We're getting to the exa. Okay, so this is huge problem. So we have the Earth Science Data Systems, but NASA is also at the same time committed toward making the data products, the code base, and conforming to as much as possible to these open science initiatives. So we're a part of that, and so this is something we're really striving to make these data sets more open. These are some tools. We already have the Earth Data Search. I think Claudia is going to mention she liked that. And Worldview, you can see some of these things, but it still relies on expert. It's not down to the application level. So this is the new strategy for trying to bring the research and these observations through the modeling and developing new applications for them, and then actually looking and developing solutions and value. So this program now has many elements. One of those is water resources. I think you're in that. It's interdisciplinary, but you're probably funded under this program, which I didn't have anything to do with giving you your money. But the kind of a new announcement is just really within the last 3 weeks, we have a new energy and infrastructure theme. And so this represents new opportunities to look at how to build partnerships and collaborations and pathways for the data to be delivered. But we have all these existing themes. There's an old applied science program, and many of these are existing. And so many of these parameters and data sets that you're using are already available, already being used by folks in these areas. And each of these will offer solicitations, right, so that you can write proposals and hopefully use. Now, in the next 38 seconds, I was just going to talk about our project, which is the cornerstone of the current energy and infrastructure, which is, we call it POWER, which is a good name. I like that name. And but we're really emphasizing taking all the data sets and making them available in ways that folks in the renewable energy community, the building energy and efficiency, sustainability communities, and agricultural can really utilize them. So what does that mean? That means taking all these data sets that we talked about, talking to the users in these various communities, going to the source, and I mentioned series, going to the source, spending a lot of time validating the source. What's the uncertainty? How is it compared to the measurements? Developing ways to process the data, like cloud-optimized formats. Everything we've put up now in the cloud, all our services are based in the cloud. And then putting these in really what we call application-ready data. So different specific formats. So if you have an existing tool, let's say you model buildings, and there are tools out there like Energy Plus. Well, you can go to our website and order the data exactly in that format, put it right in your tool. You're done. You don't have to go to Earth Data Search and try to do all that processing yourself. So that's one of the things that we've done, and we continue to partner. And soon, Joe's going to throw me off. So we do the solar, and we do the modeling data from the Merit 2. We have a complete API services to do this. We even have a user interface. A number of success stories. One of the ways to use analytics is to figure out who's using the data, where, when, what parameters, what's most important to them. This is just an example of a composite of 3 days, linking to where the people sit when they order the data to where they're actually ordering the data from. We do have users. We provide global data. We have users all over the world. And then I mentioned these data sets aren't static. They get reprocessed. So we're continuing to improve the products. We'll integrate these tempo measurements into some new products as well, in solar irradiance in particular. And then we've been doing work with the CMIP-6 because NASA has its own downscaling modeling element. So this is, for instance, cooling degree days at our location here in New Hampton, Virginia. So these are various different scenarios from the CMIP-6 pathways. You can see some of the divergence there. We compare them to the current, so we actually do a second down bias correction to try to get things currently, but we're working with all the NASA centers right now, but plan to make this available to the public. One of the things you can do, ASHRAE has these climate zones, and so all your building codes are based on your climate zone. Well, if your climate zone is changing because of changes, that's a major implication on your building regulations. So we've been showing and working with ASHRAE and showing the evolution of these zones and even the differences in time, and even at particular locations for which scenario might you change your zone. One last thing I really wanted to mention was this idea of digital twins. This is something the agency's promoting within the AIST program, which is the Advanced Information Systems and Technologies. And this is where we and here's an example. So we've been working with JPL. So we have our power data products. Those are fed into the Land Information Center system at Goddard. That model, the inputs from that model can be put into RAPID, the discharge model. And then we're working with the flood dam folks from Kness, and they're looking at different river basins to develop a framework for digital twin technology to assess and look at the potentials of floods and those processes. So this is my last slide. And so we're looking at, we have many different areas where we need advances. We need advances in the basic algorithms, and now they're looking at satellites, smaller satellites, that can actually do onboard processing. So now, how do you organize, how do you optimize those algorithms? Okay, so there's a lot of opportunity there. And then just the multi-satellite data fusion, we've already seen some of these data-driven solutions where they're combining multiple satellites together. You have to understand the attributes of the different data products and what their strengths and weaknesses are. And then dissemination, obviously, if you're a user and you want this, how do you get that? There's some advances there. And then multidisciplinary partnerships understand user requirements, making sure that we have complete information metadata on the data sets. And then these digital twin technologies, which is a real tool to explore what ifs. If you have a sets of models, a framework, and you can model an area, then you can ask questions. Well, what if this changes? What if that changes? How does that influence the likelihood of a flood or what factors? What preconditioning? And those sorts of questions as information providers need. So I'll stop there. Sorry for going over, Joseph.